Welcome friends, Igor is here, and in this video we will talk about the range of a linear transformation. In this lesson we will define the range of a linear transformation, compute the range of one linear transformation, and prove that the range of a linear transformation is always a subspace. Let's get started. Given a linear transformation, its range is a subset of the codomain. Informally, it is simply the set of all possible values of the linear transformation as a function. And here is a formal definition of the range. You take all possible inputs from the domain, you compute the values of the linear transformation on those inputs, and the set of all these values is the range. We defined surjective linear transformations in the previous video, and now we can reformulate the definition of a surjective linear transformation to the following. A linear transformation is surjective if and only if its range is equal to the codomain. In other words, every vector of the codomain is a value of the linear transformation. Let's consider this linear transformation from C3 to C5, and let's compute the range of this linear transformation. The range consists of all possible outputs of the linear transformation. A vector v is in the range of this linear transformation as long as this vector v is equal to the value of the linear transformation on at least one input from the domain. This means there must be a vector u of size 3 so that v is equal to this vector. But we can rewrite this vector as a linear combination of three fixed vectors with the components u1, u2, and u3 working as scalars. But this equation says that every value of the linear transformation t is one of these linear combinations. Moreover, the scalars in this linear combination are the components of the input vector u, and we can use any vector in the domain, which is C3, as an input. This means the set of all possible values of t is the set of all possible linear combination of these three fixed vectors. But this is precisely the definition of a span. Therefore, the range of this linear transformation is equal to the span of the set of these three vectors. In fact, we can do better than this. You can check that the set of these three column vectors is linearly dependent. Therefore, we can reduce it down to a linearly independent set which still spans the same space. This smaller linearly independent spanning set is going to be the basis for the range of the linear transformation. You may want to check out this video which explains how to reduce a spanning set down to a linearly independent spanning set. This computation shows that the range of this linear transformation is equal to a span of some set of vectors. But we also know that span is always a subspace. Therefore, the range of this linear transformation is a subspace of the codomain. In fact, this is a general phenomenon. The range of any linear transformation is always a subspace of the codomain. Let's apply the three-step test for a subspace. First, let's check that the range is non-empty. We don't know what vector space U is, but for sure it must include the zero vector. Therefore, we can compute the value of the linear transformation on the zero vector in the domain, and we know that all linear transformations send zero vectors to zero vectors. Therefore, the zero vector of the codomain is a member of the range. Second, let's check that the range is closed under vector addition. For this, let's take two vectors x and y in the range. By the definition of the range, this means there are vectors w and z in the domain U such that t of w is equal to the vector x and t of z is equal to the vector y. This is because the vectors in the range must be the values. Then, let's see what happens when we compute the value of t on the vector w plus z. T is a linear transformation, so it respects vector addition, and we know the values of t on w and z. They are x and y respectively. But this computation says that the vector x plus y is one of the values of the linear transformation t, therefore it is a member of the range. This shows that the range is closed under vector addition. Third, let's show that the range is closed under scalar multiplication. For this, let's take an arbitrary scalar alpha and any vector x from the range. Because x comes from the range, there must be an input w in the domain so that the value of t on the vector w is the vector x. Then, let's compute the value of t on the vector alpha w. T is a linear transformation, so it respects scalar multiplication. Also, t of w is the vector x, and this computation shows that the scalar multiple of the vector x by the scalar alpha is equal to one of the values of the linear transformation t, therefore this vector is a member of the range. This shows that the range is closed under scalar multiplication, and this completes the proof that the range is a subspace. We can characterize elements of the range by their preimages. A vector belongs to the range of a linear transformation if and only if its preimage is a non-empty set. This is a simple consequence of the definitions. In the forward direction, let's assume that the vector v belongs to the range of the linear transformation. This means there is an input vector u from the domain so that t of u is equal to the vector v. But this means that the vector u belongs to the preimage of the vector v, and in particular, this preimage is not empty. In the opposite direction, let's assume that the preimage of a vector v in the codomain is not empty. This means we can find at least one vector u in this preimage, and in turn, this says that t applied to the vector u is equal to the vector v. But this says that the vector v is a value of the linear transformation, therefore it belongs to the range. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discover some interesting properties of surjective linear transformations. I will see you later.